Welcome to our explainer. Today, we're literally getting our hands dirty as we dive into the fundamental origins, the composition, and the fascinating science of the very ground beneath our feet. We are going to unpack exactly how soil acts as this incredible interface between the organic and inorganic chemistry of our terrestrial world.
To really anchor our journey today, consider this profound truth. Without life, there is no soil, and without soil, there is no life on the Earth planet. It's the ultimate interface. It intercepts energy from the sun and moisture from the hydrosphere just to sustain our entire world.
Here is our roadmap for today. We'll be covering civilizations built on soil, the evolution of Earth's spheres, the Earth's crust, the anatomy of soil itself, some pioneers of science, and finally, the branches of soil science. Let's get right into it. Section 1. Civilizations built on soil. We're looking at the foundation and the downfall of societies. The survival of entire human civilizations has literally depended on the dirt they settled upon. Since the absolute dawn of agriculture, people knew the immense value of fertile river valleys. But history shows us a pretty brutal truth. The mismanagement of fertile soils is actually the primary contributing factor to the downfall of a society. Through man-made erosion or salinization, basically just from bad, injudicious management, these once thriving agricultural fields are reduced to absolute desolation. Add in the short-sighted depletion of water resources and the dumping of poisonous wastes, and we see this really consistent, heartbreaking pattern of abuse.
Moving on to Section 2, the evolution of Earth's spheres. We're zooming way out, from the cosmos to our planet.
So how did this planet even form in the first place? Back in the 19th century, two competing theories really battled it out to explain our solar system's birth. First, you have Chamberlain and Moulton's planetesimal hypothesis. They suggested a massive passing star created a gravitational pull so strong it actually tore matter right from our sun, condensing into planetary nuclides, moving in orbits. Then you have the nebular hypothesis, which argued the solar system was once this intensely hot, cloudy mass of vapor and gas in perpetual motion. As it cooled down, it condensed and threw out rings that eventually disrupted to form our planets, leaving the still incandescent central mass as our sun.
Now fast forward to the Earth as we know it, and at the foundation of everything is the lithosphere. This is the solid sphere of our planet. It's the continents, the ocean basins, the plains, mountains, and valleys. The entire interior is just rocks and minerals. And remarkably, this solid zone amounts to over 93% of the Earth's total mass.
But beyond that solid lithosphere, geographically, our planet features two other spheres corresponding to different states of matter. There's the liquid hydrosphere, which is about 10 kilometers deep, covers 70% of the Earth's surface, but only makes up 6.91% of the Earth's mass. And then there's the gaseous atmosphere. This is the envelope extending 322 kilometers high over the surface, contributing a tiny 0.03% of the Earth's overall weight.
Section 3. The Earth's crust. These are our elemental building blocks. When we actually break down the Earth's crust, the elemental math is staggering. Out of the 106 known elements, just 8 of them constitute 98.6% of the crust by weight. But here's the wildest part. Just 2 non-metallic elements, oxygen at roughly 47% and silicon at almost 28%, make up nearly 3/4 of the entire crust composition. The rest of it is mostly metallic elements like aluminum and iron.
Section 4, the anatomy of soil. And fun fact, the word itself is derived from the Latin word solum, meaning floor or ground.
Soil is formed through the accumulation of natural bodies, synthesized from this mix of disintegrated minerals and decaying organic matter. If we look at a perfectly balanced, representative loam surface soil at optimum moisture for plant growth, the breakdown is incredibly precise. You have a solid phase that's about 45% mineral material and 5% organic matter. Then, the remaining pore space is split straight down the middle. Exactly 25% volume is water space and 25% is air. Now, those proportions of air and water are subjected to rapid and massive fluctuations, and getting that mix right heavily determines the soil's suitability for plant growth.
Let's break down those specific components, starting with the biggest chunk, mineral matter. The inorganic portion of soil varies wildly in size. It includes rock fragments ranging from stones and massive boulders larger than 250 millimeters, all the way down to gravel, gritty sand, powdery silt, and incredibly fine, sticky clay, which is literally less than 0.002 millimeters. This inorganic fraction is the absolute original source of most of the essential mineral elements plants need to grow.
Next up is organic matter. Despite only taking up that tiny 1 to 6% fraction by weight in topsoil, it is absolutely indispensable for soil productivity.
Without it, you're in trouble. It's made up of partially disintegrated plant and animal residues, plus compounds synthesized by soil microbes. What's super fascinating here is that it's a highly transitory constituent. Because it's continuously broken down by soil organisms, it can last anywhere from just a few hours to several hundred years, which means it requires constant, regular maintenance.
Moving into the pore spaces, we find soil water. It's held in there with varying degrees of tenacity depending on the pore size, and it forms what scientists call the soil solution alongside its soluble constituents. This is a critical medium. It supplies nutrients directly to growing plants, while simultaneously controlling the energy balance of the soil and regulating gaseous exchange.
And finally, soil air. It occupies whatever pores aren't filled with water. Now, you might be surprised to learn that soil air differs immensely from the regular atmospheric air we breathe. Because of the moisture content and all that root and microbial activity down there, the carbon dioxide levels trapped in soil are often several hundred times higher than the atmosphere's 0.033%. Furthermore, the oxygen content is usually less than 20%, and in really extreme cases, it drops to just 5 to 10%, which creates highly unsatisfactory conditions for plant growth.
Section 5. Pioneers of Soil Science. Let's look at some early scientific investigations.
You know, for centuries, our knowledge of soil came purely from farmer experience, just trial and error. But in the 19th century, agricultural chemistry rapidly evolved. In 1834, French agriculturist J.B. Boussingault proved that air and water were actually the primary sources of carbon, hydrogen, and oxygen in plants. Then by 1840, German chemist Justus von Liebig completely threw out the old humus theory, establishing that adding minerals directly to soil increased crop yields, and he proposed the law of minimum. Fast forward to 1890, and S. Winograski unlocked the microscopic level, isolating the specific groups of bacteria responsible for nitrogen transformations in the nodules of leguminous plants.
And finally, Section 6, Branches of Soil Science, categorizing the study of our soil mantle.
Because soil is so ridiculously complex, it requires a lot of different specialized lenses to fully grasp. First off, it's vital to distinguish between two core concepts in the science, pedology and edaphology. Pedology is all about studying soil as a natural body in nature. It deals with its genesis, survey, classification, and geographical distribution without primarily focusing on practical use. Edaphology, on the other hand, specifically examines how soil influences living things from the standpoint of higher plants, including how we humans use the land for crop growth. Beyond those two core concepts, the discipline branches out immensely. We've got soil fertility, which focuses on supplying chemical elements, soil chemistry, looking at crop needs, soil physics, studying physical processes, and soil microbiology, examining that vast microscopic population. There's also soil genesis, soil surveying for mapping out the land, and crucially, soil conservation, which is the constant fight against physical loss by erosion and chemical deterioration. So, I'll leave you with this final provocative thought based on everything we've covered today. The soil serves as our environment's fundamental foundation. It acts not only as a growth medium, but as a vital sink for waste that might otherwise poison our entire environment. Yet knowing that mismanagement is the primary contributing factor to the downfall of a society, will we finally start preserving this precious mantle? Or will our population, environment, and food crisis lead to our own desolation? The careful preservation of our soil mantle truly is the difference between a prosperous society and total poverty. Thanks for joining me on this explainer.